you have exactly one measurement of Uranus's magnetic field in motion. It was taken across a handful of rushed hours, decades ago, by a spacecraft that flew past once and never came back. Since then, every model, every simulation, every assumption about how this planet's magnetism behaves has rested on that single, brief look. Now, the most sensitive infrared eye ever built has spent an entire day watching this planet in unbroken detail, and what it returned does something stranger than confirm what we thought we knew. It asks whether we ever really knew it at all. This isn't just a new image, it's new proof, and it opens a question that has nothing to do with pretty pictures and everything to do with whether decades of science were built on solid ground. By the end of this, you'll understand exactly what that single old measurement got right, what it may have gotten wrong, and why nobody can yet say which. For most of the time we've known about it, Uranus has been the planet nobody got excited about. A pale, featureless blue ball, cold, quiet, and largely ignored. That reputation was built on almost nothing. A blurry photograph. A single fast flyby. A world we glanced at once and filed away as finished business. Even the scientists who study planets for a living have described it as the least explored major world in the solar system, visited exactly once, by a spacecraft that was already on its way somewhere else. But that glance told us something that never stopped being strange. The spacecraft that passed by measured a magnetic field unlike anything else in the solar system. On Earth, the magnetic field lines up neatly with the planet's spin. The North Pole and the North Magnetic Pole are practically neighbors. Uranus breaks that rule entirely. Its magnetic field is tilted nearly 60 degrees away from the direction the planet actually spins, and it isn't even centered inside the planet. It's shoved off to one side, displaced by roughly a third of the planet's own radius. Picture a bar magnet crammed into a globe, then dragged away from the middle and jammed in at a steep angle. That's the geometry scientists have used to describe Uranus's magnetism for as long as most living astronomers have been working. Part of the reason that single flyby went so long unchallenged is simple distance. Out where Uranus orbits, sunlight arrives roughly 400 times fainter than it does here on Earth, and the planet's own glow is fainter still. Ground-based telescopes could catch only a faint trace of brightness, never enough to reveal any real structure behind it. And there was a second oddity nobody could explain. Starting decades ago, ground-based observations noticed Uranus's upper atmosphere growing colder, year after year, with no obvious cause. A planet this far from the sun isn't supposed to have much energy left to lose, yet something up there kept bleeding heat into space, quietly, consistently, for reasons nobody could pin down. For decades, that's all we had. One flyby, one faint, cooling glow watched from 100 million kilometers away, far too dim to reveal any real structure. For decades, none of it had an explanation. A planet rolling on its side, with a magnetic field that looked broken, slowly losing heat for no stated reason. But to understand why scientists finally aimed the most sensitive infrared eye ever built at this problem, you have to understand exactly what they were staring into the dark to find. An international team led by researcher Paola Tiranti pointed Webb's infrared spectrograph at Uranus and simply held it there. Not for a quick snapshot. For about 15 hours straight, nearly one entire spin of the planet, since a full day on Uranus lasts around 17 hours. That's the kind of patience no ground telescope could afford, and no flyby ever had time for. What they were hunting was faint. High above Uranus's visible cloud sits a thin, electrically charged layer of atmosphere called the ionosphere, the region where sunlight and the planet's own magnetic field strip electrons loose from molecules and produce a dim glow. Specifically, they were tracking light from a molecule called H3+, 3 hydrogen nuclei bound into a single ion, which happens to be one of the most reliable thermometers scientists have for the upper atmospheres of giant planets. Trace that glow carefully enough at enough different altitudes, and you can reconstruct temperature and particle density the way a hospital scanner builds a three-dimensional image by stacking thin slices, one on top of the other. Nobody had ever collected enough data to do that for Uranus. Until this. The team gathered over 1,000 individual altitude slices, reaching from a few hundred kilometers above the clouds up to roughly 5,000 kilometers, and stacked them into the first genuine three-dimensional map of this planet's upper atmosphere ever built. Nothing this detailed had ever existed for Uranus before, not from any ground telescope, not from that one historic flyby, not from any instrument flown since. And the moment they had a real structure to look at, instead of a flat, single number, decades of assumptions started to crack. The temperature peaked between 3,000 and 4,000 kilometers up, at around 150 degrees Celsius. That's hot compared to open space, but it's noticeably cooler than earlier estimates, confirming that the decades-long cooling trend is real, measured and still happening right now. That part at least resolved a mystery that had sat unanswered since the early observations first hinted at it. But it also revealed a new one. The density of charged particles didn't peak where the temperature did. It peaked much lower, around 1,000 kilometers up, thousands of kilometers below where the heat was concentrated. Two separate signatures in two separate places, in the same thin sliver of atmosphere. As Taranti put it, the team could finally trace how energy moves upward through this atmosphere and see the influence of that lopsided magnetic field directly. And that question about whether the old measurement of that field was ever a fair one turns out to be far stranger than anyone expected. The team's own program was overseen by fellow Northumbria University researcher, Dr. Henrik Milan, and together they had built something that hadn't existed in all the decades since that first and only flyby. An actual profile of this atmosphere's structure, layer by layer, rather than a single blurred impression. Here's what the mismatch actually meant. Something complex was stirring energy through Uranus's atmosphere in two distinct locations, and the leading suspect for why was the very same magnetic field measured decades earlier. On a planet with a clean, centered field like Earth's, auroras form as neat rings around the poles, driven by particles funneled cleanly along magnetic lines. Uranus's field is anything but clean. Because it's tilted and off-center, it doesn't funnel particles evenly at all. Webb's map showed exactly what that produces. Two bright auroral bands sitting where models predicted the magnetic poles should be, and between them, a distinct dark region where both the atmospheric glow and the ion density dropped away almost completely. That gap is direct, physical evidence of a magnetic field failing to deliver particles evenly into the atmosphere below it. Similar dark gaps have been spotted at Jupiter, where a powerful centered magnetic field controls which particles reach the atmosphere below and where. On Uranus, with a field this tilted and this far off-center, the effect is far more extreme. There was another detail buried in the data that made this even stranger. Earlier observations, including some from Webb itself, had shown Uranus's auroras as small, compact, bright spots, brief flickers of light. This new map showed something different. Bright bands stretching across roughly 50 degrees of longitude, far wider than anything a simple, tidy magnetic field would produce. That width alone is a signature of just how distorted and far-reaching the planet's magnetic geometry really is. For the first time, scientists could see just how deep that magnetic influence actually reaches, not just skimming the surface, but shaping the temperature and structure of the atmosphere, thousands of kilometers up. The mismatch between the heat and the charged particles finally had an explanation. It wasn't two separate mysteries. It was one strange magnetic process, doing two different jobs in two different places, at two different altitudes, under the control of a field nobody has measured directly in decades. Which brings us back to the deeper problem this new data can't fully answer. Because right now there are at least 3 live explanations for why Uranus's magnetic field looks the way it does, and they don't all point in the same direction. The first is the one that should unsettle you most. A recent reanalysis of the old flyby data suggests that spacecraft may have arrived during an unusually strong burst of solar wind, one powerful enough to compress and distort the planet's magnetic field, before anyone ever measured it. Researchers looked back at readings taken in the 2 weeks leading up to that encounter, and found exactly the kind of solar activity that could squeeze a planet's magnetic field out of its normal shape. If that's correct, the tilted off-center field written into 30 years of textbooks might not be Uranus's normal, everyday state at all. It might be a measurement taken during a temporary distortion, caught at precisely the wrong moment. The second explanation is the opposite, that the field really is that strange, permanently, and that Uranus's internal structure is simply built in a way no other planet in the solar system shares. Under this view, there was nothing unusual about the day the flyby happened. The planet has simply always looked like this, and the surprise is only ours. For having assumed a single planet's magnetism has to resemble the ones we already know. And underneath both of those sits a third, even bigger unknown. We still don't actually know how Uranus generates a magnetic field in the first place. Earth and Jupiter produce theirs through a churning, electrically conductive core, metal and rock in Earth's case, metallic hydrogen in Jupiter's. Uranus may not have anything like that. The leading hypothesis instead points to a deep, slushy layer, water, ammonia, and methane, compressed under crushing pressure into an electrically conductive fluid, generating a field not from one clean source but from a shifting process spread through the planet's middle, rather than its center. That alone would explain why the field looks less like a single magnet and more like several overlapping ones, layered and off balance. If any part of the first explanation is right, the implications reach far beyond this one planet. Everything modeled about Uranus's ionosphere, including how scientists are interpreting this very new Webb data, has been built on the assumption that the old magnetic measurement was representative. If it wasn't, that foundation needs rebuilding. And this isn't a small private problem. Ice giants like Uranus and Neptune are thought to be the most common type of planet in our entire galaxy, more common by far than worlds like Earth or Jupiter. Get the physics of one wrong, and you quietly distort how thousands of worlds we will never visit directly are understood. So, which explanation is correct? Right now, nobody can say for certain, and no telescope, however powerful, sitting this far away, can fully settle it. What we can say is that Uranus's magnetic field almost certainly isn't produced the way Earth's or Jupiter's is. The churning core model doesn't fit. The deep conductive fluid layer is the best explanation currently on the table. But whether the field's chaotic off-center geometry is Uranus's true permanent character or a temporary distortion caught during one unlucky flyby remains genuinely unresolved. Settling that question decisively would take something no orbiting telescope can provide. It would take a spacecraft sent back, deliberately, to watch this planet for more than a few rushed hours, an orbiter carrying instruments built to measure the magnetic field directly, and, ideally, a probe dropped into the atmosphere itself to sample it from the inside. That kind of mission is now a stated priority in future planetary exploration plans, ranked among the most important large missions scientists want to see funded in the coming years. It has not been built. It has not been funded. it has not launched. Webb didn't close the oldest question about this planet. It sharpened it. Every new layer of detail in this atmosphere doesn't shrink the unknown. It narrows down more precisely where our ignorance still sits. That's not a failure of the science. That is what it looks like when a science finally has the tools to ask its oldest question properly again, decades after it first ran out of ways to ask it. The sharpest image we've ever captured of this planet's atmosphere has also become the clearest proof of something uncomfortable. That one brief, decades-old glimpse still quietly governs almost everything we think we know about how this world works, and that the only way past it is to go back.